So today I'm going to talk about the dark room example. And this is an example I've been giving to my classes for a number of years. It helps to explain a lot of elements, particularly omitted variables bias and also the difference between causality and correlation. So this example, this dark room example, will show omitted variable bias, correlation versus causality, and the potential of mixing distributions to uncover causality. So the experiment, the dark room experiment, is a large group of men and women that are asked to walk around in a dark room with limited to no visibility. And it's observed after running this experiment that men have a much higher probability of head injury relative to women. So many more head injuries in men. The way to work this from an equation point of view is we want to define some function that sort of captures the difference between men and women's head injury probabilities. So we can have a beta x where we have a constant term and we have a beta times a male indicator, where a male indicator is 1 if the person is male and 0 otherwise. And we would expect when we estimate this model that this beta would be highly significant and positive, indicating that if you're a man, this function will be higher and you'll have a higher probability of a head injury. From a statistical point of view, you could estimate this with a bunch of different models, but if we did a binary logit model, the equation would look something like this. And again, we would plug in our estimated value of beta and we'd be able to determine the probability of each participant's probability of them having a head injury after walking around in this dark room. But is this uncovering causality? Is there really a difference between men and women, or is something else going on here? So let's look at why are men found to have more head injuries. You can think of a lot of things. Over the years, my classes have come up with all sorts of things like men have softer heads than women. But really what's going on is there's an omitted variable that's causing a biased estimate of the male indicator variable's parameter. That missing variable is height. So there's likely a low obstruction from the ceiling that is increasing the probability of injury for taller experiment participants. Since men are on average taller than women, we have a high correlation with being a male in the probability of a head injury. But being male or female is not really relevant. Being taller is. And if we look at the possible height distributions, what they might look like, they may not be normal, but I have a normal distribution here. You can see that the male distribution tends to be shifted towards the higher values. And if we have an obstacle in the room, there's going to be a larger portion of the distribution that are going to be men above that obstacle height than women are above that obstacle height. So the beta x function, if we added height to this model, this function that we had previously would now have a constant term. We'd have some beta that we're estimating that would be multiplied by height, and then we have the beta by the male indicator, what we had before. If we run this model, the male indicator beta estimate should now be statistically insignificant because really it's height that's been causing these head injuries. Now, what happens if we didn't collect information on height? Then height becomes unobserved heterogeneity. And the way that the field has evolved to deal with this is we add a mixing distribution. So the previous equation that we had with a binary logit model now becomes a little more complex because we're adding this mixing distribution that will have an average and a standard deviation. So now when we estimate this function, this beta x function, remember we don't have height now, so we're going to try to approximate that height. We have a constant term, and that constant term, instead of just having a mean as it had before, is now going to have a mean and variance and some assumed distribution. And then we'll also have the beta times the male indicator. if this mixing distribution follows the distribution of heights, its parameters, the mean and the variance of this constant term, should be statistically significant, and the male indicator variable should be insignificant now. So this mixing distribution mitigates the emitted variable bias, approximates the distribution of unobserved effects, which in this case we speculate is the height of the experiment participants, but it does not identify the emitted variable. That's something that the analyst still has to contribute. It's telling you that there's unobserved heterogeneity with this distribution, but it's not telling you what the missing variable is. So that's something the analyst still plays a role in this model. So I hope you enjoyed this little example. This people walking around in a dark room has a lot of implications on how to explain omitted variable bias and starting to understand what adding a mixing distribution can contribute. So I hope you enjoyed the talk, and hopefully I have another sort of short econometric talk coming up in the near future. Thank you very much.